is a exercise from MST 326, exercise 10. Solve this problem, this differential equation. So it kind of screams out to us that we should do separable, separate the variables. So we want to put the p's on one side and essentially everything else on the other. So the p is going to come to the left and dt is going to come to the right. So if we do that, then that's going to give us this. So the dt's are moved up to there, and the p and the 1 minus p over m is moved down here. It's quite a standard technique to separate the variables, because if you have two variables on one side, it's very difficult to integrate them. We'll leave the k there as well, because that's just going to appear on the right hand side far more easily than if I was to move it over to the left hand side, because there's already a constant there. So let's just leave the k where it is. So integrate both sides, and that's going to give me this. Now this is the result that's given in the question itself. So let me just explain that. So we can see here that you may use the fact that 1 over x, 1 minus ax dx equals all this stuff. And that's because when you take a log of something like this, 1 over x, you're going to, so when you integrate 1 over x, something like this, the answer is going to be log of it, and that's essentially what's happening here. So we're going to use the same thing, except that a is going to be equal to the 1 over m. So p is the variable, but a, instead of being ap, it's 1 over mp. So as a result, the solution is, well, the answer is minus log 1 over p, because x is p here, minus a, well, a was 1 over m. So that's it there. And we can keep going like this. We get, on the right hand side, we're going to get integral of k dt, which is kt plus c. So I've just written to the side here that the reason that's worked on the left hand side is because if you have 1 over p dp, then it becomes log p plus c. The c that you get from this integral is just automatically moved across to this side and gets absorbed into this constant. So the two constants just become 1. What from there? Well, I want to get rid of the minus on the left hand side, so log of 1 over p minus 1 over m equals minus kt plus c. Then I want to get rid of the logarithm, because I just want, what I really want at the end is p equals, and p at the moment is locked inside its logarithm, so I need to get rid of it. So to do that, I'm just going to raise it both sides to the e, so that I've got e to the on the left hand side and e to the all this on the right hand side. When I do e to the this, the e and the log being inverse functions just cancel out effectively, and leave 1 over p minus 1 over m. On the right, we've got that minus kt plus c. If I now just multiply through, I get minus kt times minus c on the top. But with indices, we can change that subtraction to multiplication, because minus kt minus c is the same as multiplying e to the minus c times e to the minus kt. That's the same thing. Now c is just a number, just don't know what it is, but it's just some number. So e to the minus c is just a number because it's just 2.71828 to the power minus whatever, 10, 20, 50, whatever. So it's just some number. So we're just going to call that a. In the solution they call it b, but it doesn't actually matter what you call it. So we get a e to the minus kt. And sorry, I forgot to put the modular signs on that. Okay, so that's what we got so far. 1 over p over 1 minus m, minus 1 over m equals a to the minus kt. So going to the next page, that's what we've got. 1 over, if I move over the 1 over m, I'm going to leave me with 1 over p, because that's what we want. So at the end of it, we want p equals. So I need to now get rid of the 1 over m. So I'll just move that to the right hand side. I'll put a plus or minus here to show that I've taken it out of the modulus sign, because it could have been either because of the modulus sign. So that's the next part. For this part, because I've called this constant a, I don't actually need this minus sign because it could have been either. So whatever one it was, I can absorb that because it could be, if it's a negative number, it doesn't matter because I just call it plus a negative number. So I've just simplified that to a plus. So I'll just cancel that out. Here I'm going to explain in a second. So we end up with p is 1 over m plus a e to the minus kt to the power minus 1 because I need to take the reciprocal of this because, like I said, we want to end up with p equals at the end of it. On the right here, in the question, or the solution, it says we could take p as m as a solution for the original problem. Because if p was equal to m, I've got m divided by m here, and that makes 1, so 1 minus 1 is nothing, and so we just get nothing on the right hand side. And if p is equal to m, its derivative with respect to time is 0, so we'd have 0 on the left hand side, 0 on the right hand side, so that is a possible solution. But when we actually solve it, if t is equal to m, if this is equal to m, p is equal to m, it doesn't make sense because if we do the reciprocal of 1 over m, okay, that gives m, but there's this extra bit as well. So the only way that could happen is if a is equal to 0, which is what I've written there. So I hope you're following this so far, but this is almost correct. You know, if we take the reciprocal of 1 over m, we get m, so that would work. But because there's extra bit here, the only way that it could happen is if a is 0, then that gets cancelled out. But there's no reason to think that a is 0, so we'll just take it that it isn't. I mean, unless we've got a reason to think a is 0, which we don't, we can't just take it to be that. So we continue on. We're given that p of 0 is 2m, so this is the next thing. So this is the general solution of the differential equation. Now we're going to find the particular solution by actually putting in a value from which we'll be able to figure out what a is equal to. So, but 2m is equal to 1 over m plus a e to the minus to the 0 because t is 0 in this particular solution. That's the minus 1. So that's going to give us 1 over 2m is equal to 1 over m plus a to the minus 1. Oh, sorry, I've done it on mathematics. So 1 over m plus a, and then the reciprocal of that is 1 over 2m. So I've just done the left hand side. Then what I need to do is a little bit of fraction work. I'll just change the 1 over m to 2 over 2m. I'll move it over to the other side. So 1 over 2m, take away 2 over 2m is a. And that's going to be equal to minus 1 over 2m. So from that, I can put in this solution. So p is equal to 1 over m minus e to the minus kt over 2m, because that a is equal to minus 1 over 2m. So minus 1 over 2m. And then the reciprocal of that. So to the power minus 1. Don't know what's going on there. Okay, so that's that. So that's what we have now. Then the question asks, what happens when we find it? No, that's not it. There we are. What happens to the solution p of t as t becomes large and positive? So as t becomes large, what happens? It's quite a common question with differential equations. So if t becomes very, if we write this in a different format, so if I add the fractions together, right, so I change that to 2 over 2m again, so that I can add these two together. You get minus e to the minus kt over 2m, and add them, so we get 2 minus e to the minus kt all over 2m. Then take the reciprocal, so 2m over 2 minus e to minus kt. That's what p is equal to. So as t tends to infinity now, gets very large, in other words, what's going to happen? Well, that's just going to disappear. It's going to go to nothing, which is quite a common situation in maths. So I've just drawn a little graph there to show you what it looks like. E to the minus kt looks something like that. So as time continues, it's going to disappear to nothing. So that's going to disappear. So we're just going to be left with 2m over 2, which is equal to m. So at the end of all that, you find that actually the solution is m, but only as t tends towards infinity. For smaller values of t, that's not the solution. This is. Right, I hope that all made some sense, and if you've got any more questions, just ask me.